Hello there. So today's lecture, we're going to first start talking about the idea of the linear phase requirement. But before we get started, remember that what I've done is I've posted these pre-scanned notes so you can access them on the web page. Um, and inside that package is the little extra 5-point um, homework assignment that I recommend you download it and print it and kind of have a look over it before you look at the lecture, because they're just some multiple choice, easy questions that you can get from watching this thing. All right, well let's get moving. We decided in class that the ideal filter, here's the ideal filter, has a frequency response that looks like this, and looks like it fell off the end, but basically it's a constant gain for all omega. Okay, so that's the gain factor. And the exponent there is the phase term, and here it is written out. It isn't clipped, so it's minus omega times n sub d. Um, this is called the linear phase requirement. If we violate the constant gain requirement, we get amplitude distortion, and if we violate the linear phase requirement, we get phase distortion. This one we talked about constant gain, and it's pretty easy to understand how it can distort something like an audio signal or a communication signal. But we're going to talk about phase for a while. Um, what I want to remind you of is time delay and phase are the same, very same idea. This is kind of a time domain representation, and this is a frequency domain representation, but it's the same thing. And the easiest way to see that is just to look at a really simple example. Here's just a regular cosine. Let's say we delayed this cosine. So the original cosine might just look like this, you know, do that sort of thing. But if we delay it, it's now shifted to the right, so it may peak there. So there's a shifted cosine, and it's shifted by nd samples. So everybody understands a time delay. Whenever any signal goes through a real-world kind of system, it gets a time delay. Um, well, let's just plug it into here. If we replace n with n minus n sub d, we get this. That just clearly follows from there. And then if we factor this, we just distribute omega across, so we get omega times n is the time variable, minus omega nd, nd is just a constant. We get a form that looks like this. And we see this thing here now has takes the role of a phase shift. So we can write the whole output looking like this. Okay, where theta is the same as omega nd. Well, all right, so what we've shown is a time delay of nd samples and a phase shift of theta equals minus omega nd radians are the exact same principle. So they're just two different ways of saying the same thing. So don't worry about phase. When people tell you about phase, don't worry that you don't understand it, because you do understand it. Here's an example of linear phase. Um, Frequency in omega is on this axis. Phase is on this axis. Um, Phase is an odd function, so it always goes through the origin. So I'm not drawing the negative frequencies here for this example. So it's just a straight line. Theta is equal to minus omega nd is just a straight line with a negative slope. And the negative slope, if you look at this equation, the slope is equal to whatever multiplies omega. And we got a minus sign there. So the slope of this line is equal to delay. So this is a linear phase system. Any system that has phase, that's a straight line through the origin, is a linear phase system. And the result of a linear phase system is no phase distortion. Okay? Okay, I've hopped to the next page. All right, now that we understand phase, remember that we went through a lot of trouble to be able to write the frequency response in terms of a purely real function multiplied by a complex exponential. So this complex exponential carries most of the phase information unless A goes negative or positive, then there's some sign information in A, but this A is purely real. The phase of the frequency response, written here, is equal to the phase, is equal to theta, this part, without the J, plus any plus or minus pi whenever this thing goes negative. When this thing is, whenever this thing goes negative, we pick up a plus or minus pi. Whenever this thing is 0, it doesn't make any change to the basic phase thing. All right, we call theta of omega is the continuous phase part of this. These plus or minus pi contributions from A are phase jumps. So every now and then, whenever A goes negative, we might pick up a plus or minus pi in the phase diagram. We can also get phase jumps when the computer decides on its own to wrap the phase values to keep them inside the principal range. Now your calculator does this as well. When you do a calculate a phase, it's always going to give you a result that's between minus pi and plus pi, or minus 180 and plus 180. This is called the principal range. And so these phases are called principal phases, or wrapped phases. And the way it does that is it just takes the original phase and adds plus or minus multiples of 2 pi in order that the result winds up in this principal range here. Okay, so we can always add plus or minus 2 pi to anything, and we're not changing the phase in any way. But the results that a computer give you, or a calculator give you, or MATLAB are always in this principal range. So here's just sort of a graphical example of that. Here's some phase function. Obviously, it's not a linear phase function. And it's just sort of coming down. This is a continuous phase. This is a continuous phase. It's got no phase jumps. The unwrapped phase is another way to say it. So we've left out all the phase jumps. But you see what happens is if you calculate this on a computer, it's not going to give you results that are outside of this principal range. It's going to add plus or minus 2 pi to it, which is fine. That doesn't change the phase, but it does give you these weird sort of phase jumps. So this is called wrapped phase or principal phase. All right, so why do we worry so much about phase and wrapped phase and unwrapped phase? And what I want you to be aware of is when you see a phase plot that has all these funny jumps like we have up here, they may not match your theory that you derived when you were working your problem. It may not be what you expected, but probably, there's a good chance you did it right. And it's just that it's wrapping around the phase that you expected and forcing it into the principal range. So that explains something you'll often see. The second reason is I need unwrapped continuous phase. I need you to understand that idea for the discussion that's coming up here in a second. All right, I've shifted to the next page of the notes. What we're going to talk about now is called group delay. Remember that phase and delay are the same thing. So, and that the slope of the phase line is equal to delay. Well, we can just formalize that. That's been formalized. It's just what's called group delay, and we're going to call tau sub g, and it's a function of omega, and it's just the minus, because we want to get rid of that minus sign, the slope of the phase function. So that's called group delay. Okay, that's a real simple thing. It's just the slope. But we have to have theta here. We have to have continuous phase because we can't have phase jumps if we're going to be taking a derivative. So that's one of the reasons we spent so much time on that. Right, here's a simple example. Suppose you have a phase function that looks like this. It's nonlinear phase. It will distort the output, will give us phase distortion. So two different slopes. If we take the derivative of this thing, it's clear that the slope in this region is -1, so the group delay is +1, because we get rid of the minus. We have a minus, we get 1. And the slope here is a -3. So a -3 in this range is 3. So we have one sample of delay. These delays are in samples, so that's one sample of delay here and 3 sample of delays for any signal in this frequency region. So a real simple example, real quickly, suppose I have the sum of two cosines at frequency omega1 and omega2, and here I've shown omega1 and omega2. If they go into this system that has this phase response, the output is going to be this. The cosine whose frequency is omega1 is going to experience a delay of 1 sample, so that's how we show that, 1 sample of delay. And the cosine whose frequency is omega2 is going to experience 3 samples of delay. So that's how we write that thing. And when we add this together, this thing is going to look a lot different than this thing because we've got this phase distortion. Well, here's another example. Find a group delay if h is given by this thing. And this is the kind of thing we've done before. Just take the Fourier transform, discrete time Fourier transform, and we get this. Okay, the -2 is because this is n equals 2, and this is n equals 3, that's for that term, and this is n equals 4. So we get this term. We factor out e to the -3j omega, like we've done in class, and we use Euler identity to combine those two guys into cosine omega. So this is the continuous phase representation that we worked on. So the continuous phase is -3 omega. That comes from that exponent. We drop the j. So there's no j in the phase thing. Group delay is minus the derivative of this. So the group delay is just 3 samples. All right, so I went through that quickly because it's stuff we've done before. The only thing we haven't done is taken the derivative of something that simple. Well, what's it all mean? Remember, h is just the system response when the input is a delta function. That's the definition of the impulse response function. So if the input is a delta function, goes into h, and here's the output. This is just these guys I gave you, right? This is 161 delayed out to the right. So this is 6, and these guys are at 1. That's not a -1. That's just a line showing that. So we get, this is the impulse response. It should look as though it takes about 3 samples for the biggest part of the energy to get through this system. That's the group delay. We found the group delay is 3. That's how much time it takes for the energy to get through the system. And notice it smears it out, so it all isn't happening at once. But the group of energy is getting through the system in 3 time steps. Well, finally, I'm going to finish up this video because it's going kind of long. Back to the linear phase requirement. This is the requirement to avoid phase distortion. We need the group delay to be a constant. Okay, this is linear phase. If we take the derivative of this, we get a constant. That's the requirement for no phase distortion. What that means is that all frequencies experience the exact same delay. Okay, so that's the end of this talk. Sorry, it went a little long.